All right, this section of notes is going to be on transformations. This is 2.6. And remember, 2.3, 2.6 are together as one day, but I just separated the videos to kind of make the time work out well and give you kind of the two different looks at it. So transformation is nothing new for you guys. We've done this in Algebra 2. We're talking about taking a graph and moving it left, right, up, down, reflect over the x-axis, reflect over the y-axis, and then stretch and shrink. In Algebra 2, you called it dilate to make it bigger and smaller. We're calling it stretch and shrink. That's what this book uses, so just get used to that terminology. Let's kind of walk through the slides, the first couple slides, sort of quick, just to kind of remind you guys of what kind of transformation is caused by whatever change in the function. So if you take a function and you add something to the function itself, and we think of f of x actually as y. I know it says like y equals f of x, but we think of this as being the y value. So if you add something to a y value, you'd move that point up. Think of it as a coordinate. If you subtract something, you'd move it down. So vertical changes, they do what the numbers say they do. So positive up, negative down. And that's kind of all there is to show you there. We'll get to see it in action here in just a few minutes. Left and right, which is a horizontal change. Left and right, or horizontal changes, I should say, they tend to have kind of an opposite effect. So we'll talk about how that is, but now you're changing the x value. So when I change something to do something to an x value, that's a horizontal change because x is horizontal, so that's how I know I'm working with a horizontal shift. So a change in x, horizontal. A change in the function value, or y, vertical. Now, why is it that minus c goes right and plus c goes left? Because your brain will tell you the opposite, right? You think if I was moving negative on an x-axis, I'd be going left. Positive on x-axis, I'd be going right. Yet these changes are opposite effect. And for a pretty simple idea, if you take what's in parentheses there and you set equal to 0 and solve for c, all of a sudden you can see that that's positive c, and positive is going to the right. So it's because it's attached to x, almost like a factor. Think about how you solve factors when you set them equal to 0 and solve. And of course, the sign changes when you do that. It's no different here. So really, x minus c, as you see it here, would be x equals plus c, which is a right movement. So when you look at it, you got to think opposite, but here's the reasoning for that in terms of direction. Then we got our reflections. You can reflect over the x and reflect over the y, and this is more about coordinate geometry, kind of thinking about what affects the coordinates when you do the reflection. So let's start out with, we'll go over the x-axis. So I'm going over the x-axis, and this is my original point, and I reflect it, which now puts it down here. What changed in the coordinate? Well, if you think about it as just coordinate itself, the y value changed to negative. So the basic idea is then kind of work it in reverse. When I make my y value negative, I reflect it over the x-axis. And here's the visual reason why that is. Then the flip side of that, when you go over the y-axis, well, think about this coordinate now reflected over the y-axis. What changes? It's a sign on the x value. So the rule would say then in reverse, what we saw there, make your x value negative, reflect it over the y-axis. And here's the visual way to make sure you're clear on that. Of all those transformations you're going to do, I think it might be kind of easy to get these two mixed up. So, be thinking about what you're changing. I think that helps a lot. And maybe a little bit of memorization wouldn't hurt too. All right, stretching and shrinking. Now, I think of all this stuff, stretching and shrinking is, again, well, it's all coordinate-based, really. But vertical, again, does what the number says. So when you multiply, now, you're multiplying like dilating. Think about an object gets twice, 3 times its size, or it gets half its size. That's a multiplication. So now you're going to be multiplying a number by either the function, which is y, or the x value, which is going to be like your horizontal. So think of multiply by the function or y value, vertical change, multiplied by x, horizontal change. So the number out front, which we're calling c, is the one that has the effect. If c is bigger than 1, that's like 2 times, 3 times, 4 times the size. It's going to stretch it out. If a number between 0 and 1, like a half, 2/3, 3/4, going to get smaller. So this is how we determine our stretching and shrinking. So we're going to use the word stretch. And again, in Algebra 2, you said dilate, but we're going to say stretch by a factor of what? Shrink by a factor of what? And c is the factor, the multiplier. Okay. And we'll show you all this in action, like I said, in just a minute. And then lastly is the horizontal stretch and shrink, and they have a reciprocal effect. And that's, again, better when you see it in action, but when your c value is bigger than 1, it actually has an effect of 1 over c on the horizontal or on the x. So it'll shrink it down. And then when c is a number between 0 and 1, it'll actually stretch it. So again, think of vertical, the number does what it says. Horizontal, left, right, opposite, stretch, horizontal stretch, or shrink, reciprocal. Okay, let's see them in action. That's, of course, the best, is to have all the visual stuff in front of you. So what we're not going to do is have like a parabola, absolute value, a square root, a circle, you name it, what you did in Algebra 2. We're going to have generic function notation and use a piecewise graph to talk about it. So this is the function. I'm not concerned about a specific type. And then here is the transformation. So it's your job right away to just interpret what this means. Well, x plus 3, okay, so we're going to the left. So there's my blue graph, move to the left, and I'm just moving the coordinates. Piecewise is easy to do transformations with. Just move your coordinates. A transformation here is something tacked onto the function, or a change in the y value. So if I'm going to go subtract 4, that's actually down 4. Blue graph, down 4. Again, really easy to do. When you do the transformations one at a time with a piecewise graph, they're pretty simple. It's when you kind of mix them together and have multiple transformations, then there's a little bit of trying to follow the order of what's going on, but one at a time it's going to seem pretty easy, I think, at first. So again, reflections, which one's which, right? Okay, so here we go. If I change the sign on my f of x, which is changing the sign on y, then I got to reflect over the x-axis. On the other hand, if I change the sign on an x on a coordinate, that would cause it to reflect over the y-axis. Reflections are, it can be counted as just like doing up, down, left, right. You just have to count to the axis that you're reflecting over. So for example, let's say I'm in the blue and I want to reflect over the x-axis and I want to get to the red. Well, if I count 3 to the x, then I'm 3 on the other side. And if I'm 4 to the x-axis, then I'm 4 on the other side. If I'm going to reflect over the y, let's say I'm at blue and I go 1, reflection, 1 on the other side. So you can do it as a counting to help you. Visualizing, of course, works fine, but think about it as counting to the axis you're going to reflect over, and you should be good with that. Again, it's just about keeping these two straight. Which negative, based on where the negative is placed, which effect is it having? Okay, let's get into stretching and shrinking. So stretching and shrinking, again, is based on a scale factor. So you can think of it as dilate. That's how you guys talked about again in Algebra 2. So it's size it up, upsize, downsize. Vertical changes, when you change f of x, you're changing y. So I know it's a vertical just to start out by, that's where the number is placed, I guess is a good way to think about it. And then a multiplier of 2, which means we're going to get bigger. Now I'm going to base this more on coordinate than any kind of counting technique. Left, right, I can count. Reflections, I can count to the axis. Stretching and shrinking, you're not counting. You got to basically say what's the change in the coordinate. So if it's a change in y, I must go through and change all my y values by the scale factor. So by a scale factor, 2 means this. Double it, double it, double it, double it, and then replot. So vertically stretched out. So it's kind of like I can grab on to sort of the tips of the bottom and top of the graph and pull it with my hands apart and stretches out. You kind of a little bit weird with a 0 because that doesn't have an effect. But so maybe it looks slightly different than you think it would when you start trying to visualize it, but there you go, there's your stretch. And then a shrink, a half, so do the same thing. Take all your coordinates, your originals up here in red, and go half, 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 and half. And so that's like me taking the red between the palms of my hands, top to bottom, and pressing together and squishing it down. Vertical shrink. Okay, let's hit horizontal and show you how that works. So again, remember horizontal is reciprocal, so I've got my original set of coordinates again all lined up, ready to go. So now when I see multiplied by x, that steers me towards horizontal, but it's reciprocal effect. So this actually has an effect of a shrink by 1/2. And now remember what you're changing. You're changing x, so half of my x values, half, 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 and replot. So now it's like I've got the red graph between the palm of my hands and I'm pushing them together left to right. Squish it together that way. So horizontal shrink. And then, for the same thought process, now 1/2 is actually going to have a doubling effect, so reciprocal. So again, take my original reds up here, my x's, and double, 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 double. Replot. Now I'm pulling it apart horizontally, stretching it out. So left, right, up, down, and reflect, counting. Stretch and shrink, modify the coordinates. It's not really something that I would want to try to count and think I would get it accurately just by in my head or compared to an axis. Okay. One last little category of stuff we got to hit. So this is not necessarily a transformation. It's actually a classification. Oh, sorry. Classification coming next. Backtrack. We're going to go ahead and talk about this one for a minute. So build in the transformations into a base function. So here's like your parent, right? Your parent function. We talked about them in Algebra 2 as parents. So cube root of x. And then here's a list. And so insert the things in this list into the problem and create the new function where the transformations are in there. So as I read it, we'll start throwing stuff in. Reflect over the y-axis, so if I reflect over the y and to make my x value negative. Shrink vertically by a scale factor of 1/2, so vertical is going to be a change to the function, so that's got to go out front. And then a vertical shift of 3, so we're talking about up. And there we go. Basically, I inserted my transformations into a parent function. Okay, now on to our last topic, which is even odd, which is a classification. So even odd are types of functions. And actually, what they say is what they really are. So we're going to go by exponent for the most part. If you got an even exponent, you got an even function. If you got an odd exponent, you got an odd function. But we want to talk about what that means in terms of visual and then how you can test it. So even functions are like your face. They have XY symmetry or left-right symmetry, or I should say Y-axis symmetry. So look in the mirror, put your hand on your nose, and look at the left and right side of your face. And with the exception of maybe some small differences, for the most part, each side looks like the other, right? So your face is an even function. On the other hand, odd functions have what are called rotational symmetry. So that's with respect to the origin. So if I took this piece here, this half, let's say, and I just spun it at the origin and rotated around 180 degrees, I'd land on the other piece. That's rotational symmetry over the origin. So that's a visual way of knowing what you have. We'll talk about this stuff in just a sec. Okay, so how do you test? Let's say you don't have a visual and you just want to test it out. Well, basically what you do, and I'm going to translate this into words, is you test by plugging in negative x. This is for both of them. What you do is you plug in negative x into the original function. And so I'm going to replace x with negative x and then square it. And if the result is actually the original, by plugging in negative x, you've got yourself an even function. On the other hand, if you plug in negative x to an odd, and the result is negative of the original, that's an odd function. So this is a way to test, although I think you guys are basically going to be looking at, for the most part, if it's got an exponent, even is even, odd is odd. So it might be like a piecewise graph, where you have to do something with even odd, or then the connecting to an exponent doesn't work, and you got to think about the visual aspect of it. But if I got to think about the visual, then I'm just going to go symmetry. So if it's even, I've got y-axis symmetry left-right. If it's odd, I've got rotational symmetry around the origin. So last problem to look at is, just to be clear on what this is saying, what you've got is the right half. So here's the right half of the graph. Visually, here's the right half of the graph. Your job is to draw the other side. So here's the other side. So again, positive half, there it is. You draw the negative half. If it's even. Well, if it's even, it's got y-axis symmetry, so there's the even. Again, if I just visualize my y-axis symmetry. Now, draw the other half if it's odd. Well, if it's odd, it's got rotational symmetry, which means if this is my original, I've got to take that and rotate it around the origin 180 degrees, and it lands over here, and there's the odd. So in combination, green and red together is an even. Blue and red together is an odd. And all this question is asking you to do is draw the other half based on it being one or the other. Okay, that's the end of the notes for transformations. We'll call it good right there.